All right, so we are jumping ahead a bit after chapter 5, and we're looking at chapter 5, chapter 4. We're looking at chapter 9 now. So this is going back to something that we looked at, I believe it was in chapter 2. We looked at inequalities, and we did touch a little bit in those sections about compound inequalities. And 9.1 is really kind of breaking those open and going into more depth. So we have 4 objectives in this section. The first is to find intersections of 2 sets. The second is to look at and solve compound inequalities. Specifically, compound inequalities that have the phrase "and" in them. And then we're going to look at finding unions of 2 sets. So intersection and unions are 2 set theory constructions between sets. And so when I say intersection and union, those are a mathematical operation on sets of things. And it turns out it's very useful when we're talking about compound inequalities to have that knowledge under our belts. And the fourth and final objective here is to solve compound inequalities specifically with the "or" phrase in them. Now, if I'm remembering correctly, almost all of our compound inequalities we saw in chapter 2 were of the "and" variety. And the "or" variety just tells us something a little bit special about their solutions. So we'll get there in a little bit. But first, let's define intersection. So as I said, this is a set theory construct in math, and it is an intersection of 2 sets as its official name. So if we have 2 sets, A and B, the intersection of these 2 sets is the set of all elements common to both sets. So that means everything that's in A and, key in there, everything that's in B. So we denote intersection with this capital upside down U looking thing. So this is read A intersect B. And this is the set of X, all X, such that X is in A and X is in B. So this funky little symbol here and here, this is just read as in. Or you can think of it as is in, I guess would be a better. So this little symbol just says X is in A, X is in B. Technically what it's saying is that X is an element, because X need not be a number, but for our purposes, is in is plenty official and correct enough for what we're doing. So let's look at some examples. First, we'll just look at forming an intersection, and then we'll look at solving some inequalities. So if A is the set of all X such that X is even and X is strictly between 0 and 10, and then B is the set 3, 4, 5, 6, 5 intersect A intersect B is what we want to find. Now when you have sets that are defined clear like this, finding the intersection is relatively straightforward. So we look at our set here. So A is the set of evens between 0 and 10, so that's 2, 4, 6, and 8. Those are the actual elements. Those are the numbers in A. And B is, of course, 3, 4, 5, 6. Just rewriting it there. And so all you do is, the way that I like to do this is just cross out things that aren't in common. So there's no 2 in B, there's no 3 in A, there's no 5 in B, or there's no 5 in A, there's no 8 in B. And so if you do by elimination like this, you'll be left with what your intersection is. So A intersect B is the set 4, 6. And that's it. So now moving on to solving. So as you can imagine, solving this inequality and solving this inequality, we know that these are going to be inequality solutions, which means that there's a lot of numbers that do work in these inequalities. The and here is actually telling us that we are finding an intersection. So our solution is both in here and in here. So we'll talk about that in a second. So the first thing we do is solve these individually. So I'm going to add 7 here. I'm going to subtract 2x. I'm going to minus 1 here. I also need to add 7 and minus 2x both sides. And we're going to have negative x is less than 7, and 2x is less than 8. So then we divide everything by negative 1, divide everything by 2. Now remember, when you divide an inequality by a negative, you have to flip your symbol. So this is x greater than negative 7, and this is x less than 4. And we take this and symbol, and we stick it right in there. So our solution is x is greater than negative 7, and x is less than 4. And so where the intersection part comes in now is, if you think of these as intervals, this is negative 7 up to infinity, and this is 4 back down to negative infinity. And what we're actually doing is intersecting these two. And so on the number line, if we were graphing this, we'd have our 0, this would be 4, and this would be negative 7. And so we know that we start here and go up, and from this set we end at 4, so that means we stop at 4, and this is the solution on the graph that we have. We could even combine these inequalities into one, since x is both less than 4 and greater than negative 7. So this is the type of compound inequality that we saw, if I'm not mistaken, in chapter 2. Here's the solution as sets. So when you have an and, that means that we put a intersect symbol, and then we can change the inequality to a compound inequality with two symbols like this, and our graph of our solution is strictly in between negative 7 and 4. So let's try another one here. So 2x greater than or equal to 0, and 4x minus 1 is less than or equal to negative 9. So we're going to divide this one by 2. I'm going to start on this one by adding 1. So this gives us x is greater than or equal to 0. This gives us 4x is less than or equal to negative 8. Divide by 4, so we get x is less than or equal to negative 2. There's an and that comes down. So x is greater than or equal to 0 and less than or equal to negative 2. And so now this is 0 with a bracket up to infinity. And it's intersected, because it's an and, with negative infinity up to negative 2 with a bracket. So the reason that we force students to graph things so frequently with inequalities and sets is, if we graph this inequality, here's 0, here's negative 2. We start at 0, and it goes this way. We start at negative 2, and it goes this way. Well, since this is an intersection, do these two things ever actually overlap? Up here, they connected nicely into this nice set, but here, there's no overlap. So there's never going to be a value that we can plug in that is both greater than 0 and less than negative 2, which you can't see if you just stop at your inequalities or at your intervals. So this actually has no solution. Or we call this the empty set. So the empty set is just the set of nothing, or no solutions. So you have to make sure that you're graphing your solutions to double check that you actually have a final answer, because sometimes, sure, we get here, this inequality, this interval, it looks good. We have our intersect sign, everything seems on the up and up, but when we graph it, we realize there's no actual values that are going to be in both of those. So we have two more ands here. So this one, divide by 4. We're going to subtract 2. Both sides on this one, so we have 3x is greater than 6. We have x less than or equal to 0. Divide by 3. X less than or equal to 0, and again, because that just comes down with us, x greater than 2. So again, as intervals, this is negative infinity up to 0 with a bracket, intersected with 2 on a parenthesis up to infinity. And much like the last one, when you graph this, here's our 0, here's our 2. At 2, we go to the right, and at 0, we go to the left. So again, there's no solution. Which, once more, we wouldn't see unless we graphed our solutions, our intervals. Okay, for the last one, it's already in its compound form, or its shorthanded compound form. So we've seen this back in chapter 2. If I subtract 4 and we have two inequality symbols, we subtract 4 from all 3 pieces. So this is negative 2 less than negative x less than 3. Then we divide the whole thing by negative 1. We get 2, flip this symbol greater than, x, flip this symbol to greater than, negative 3. And we typically don't write inequalities like this. We always rewrite them to the smaller thing, because this tells us our interval is negative 3 to 2. And it gives us the left bound and the right bound. That's why we always switch it. And if we were to graph this, this is our 0, here's negative 3, here's 2, a parenthesis here, and that would be our solution graph. So the big thing here is making sure that you are going all the way to the graph, because when you have no solution, you might not see it until you actually go to graph those inequalities. So the other type of compound inequality is the OR compound, which is built off of the union of two sets. So if you have two sets A and B, the union of the two is the set of all elements that belong to A or B. Key in there on the OR. A union B is denoted as A with a capital big ol' U thing here. B, and this is the set of X, all X, such that X is in A or X is in B. So if you were wondering back at intersection why it's the upside down U thing, it's because union was come up with first, I believe, and so they used a big U as the symbol, and intersection is a logical opposite of union, so whoever came up with it decided, well, why don't we just turn it upside down, because upside down is like opposite, sort of. Never claim mathematicians were smart at naming things. So again, here we're just forming a union so we can get an idea of how it works. So it's the same two sets, so A is still the even numbers from 0 to 10. So that's not including 0, not including 10, so 2, 4, 6, 8. And so now when we form A union B, instead of looking at and eliminating things, we just look at everything that's here, list it out, everything that's here, and list it out. You don't repeat things though, so 4 and 6 are repeated. We don't list those. So this would just be 2, 3, 4, 5, 6, and 8. Right? You just list everything that you see. So when we solve inequalities, compound inequalities with OR, these are the things that have unions in them. So solve 5x minus 3 is less than or equal to 10, or x plus 1 is greater than or equal to 5. We just solve them individually first. So add 3 here, subtract 1 on this one. So we're going to get 5x is less than or equal to 13. X is greater than or equal to 4. Divide everything by 5. We have x is less than or equal to 13 over 5. The OR comes down. X is greater than 4. And so as intervals, this is negative infinity up to 13 over 5 with a bracket, union, bracket 4, up to infinity. And so when we graph these, let's put our 0 over here. 1, 2, 3, 4. 13 over 5 is a little bit less than 5, so if I extend this a tad, that would be where 5 is. 13 over 5 is 2/5 shy of 5, so this is here. So that means we start here and go this way, and we start here and go this way. Well, since this thing is to the left, this interval starts to the left of this one and goes right, and this one starts to the right of this one and goes left, this actually is equivalent to all real numbers, negative infinity to infinity. Or the symbol for that, because math loves its symbols, is this weird looking R with the extra leg in it. And again, just like with intersections that have no solution, unions always have a solution. If you can't see from your intervals that it's all real numbers, you can just graph it like we did above, and you'll see that it is all real numbers because everything on the number line gets crossed over. Okay, so on this last one here, again, it's an OR. We're just solving individually, so add 5, add 5. We're going to divide this one by 6. This gets us negative 2x. It's less than 2, and this gets us x is less than 0. Divide by negative 2. We flip our inequality symbol since we're dividing by a negative. We get x is greater than negative 1, or x is less than 0. So as inequalities, this is negative infinity up to 0 with parentheses, union, negative 1 up to positive infinity. And on the number line, we put our 0 here, negative 1 here. We can put 1 just for fun. We put our symbol here and go left. We put our symbol here and go right. So we can see that this is, once again, negative infinity to infinity, or all real numbers represented by this weird looking R symbol. Now, not every compound OR inequality is going to be all real numbers. Sometimes you get separate ones. The interesting thing about OR compound inequalities is if you get a situation like this example, where they go in opposite directions, it's still a solution. When you're intersecting sets that don't overlap, you have no solution. But when you are unioning them, so if we were doing negative infinity to 0 union 2 to infinity, that would be the answer. You have two disjoint, as they're called, sets, meaning they don't touch each other. So that's the end of 9.1. In the next section, we'll be looking at a special type of equation.